So what we've come to now is a section called Kinetic Molecular Theory, and it's probably one of the densest sections in the textbook. And I don't require that you know all of it. Really, what you need to know is on slide one of this set of three. And then I'm actually going to skip the next two. And honestly, if you want to know about it, we can do office hour and talk about it a little bit more. Uh, but for most people, this one slide will give them all the information they need to know. And really, in kinetic molecular theory, it's a mathematical way of understanding how gas molecules create pressure. Intuitively, I think you already understand that right now. Intuitively, what happens is gas molecules in a container are moving with a velocity and they strike a wall, and when they rebound off the surface, they impart a force onto the walls of the container. Now, if there are more gas molecules, right, there'll be more pressure because pressure is the amount of force divided by the area. But if the density of the gas molecules is lower, then the pressure will be lower because there'll be fewer collisions, for example. So the basic assumptions of kinetic molecular theory, they often call these postulates, are that gas molecules are very small. So the container in the volume, okay, is not actually occupied by gas molecules, which is kind of weird to think about, but it's kind of true. Gas molecules are really small, okay? And so most of the space in a gas is actually empty. So gas molecules are negligibly small. That is, they're so small they don't actually occupy any volume. That's one postulate. The second one has to do with the energy of the molecules. The average molecule's kinetic energy is proportional to temperature. Okay. Now, and then to back it up even further, the idea of kinetic energy, right, is Ke equals 1/2 mv square, and that's really, you don't really need to know that expression in all that much detail, but that's the equation for kinetic energy, and m is the mass, okay, and v is the velocity. So when we say average molecule kinetic energy is proportional to temperature, that means if I increase the temperature, I increase kinetic energy. So T and is proportional to kinetic energy, and vice versa, which is proportional to the velocity squared and the mass. Okay. Now, what that means then is as you heat a gas, the molecules of the gas, or the atoms in the gas, will move faster, not proportionally faster, right? You have to do quite a bit to the temperature to get the velocity to increase more because it's with the square of the velocity. That's a 2 there. So it's proportional to temperature. In this case, it's not direct. The velocity is not directly proportional. But that's another reason why, as you heat a gas, you increase the kinetic energy of the molecules, creating more pressure inside a container. The other thing that we say, the other postulate that we have, which has some sort of stipulations with it as well, is that all collisions are elastic. So when these molecules bounce off the wall, or if they actually collide off each other, as you can see there, right? The collisions that take place are elastic. Now, what does that mean? That means when they come in and they strike the wall, and then they leave the wall, or the two strike each other and then leave each other, the total energy that the molecules has is the same. No energy is lost. Now, part of this is in fact due to the idea that there are weak interactions between gas molecules. And another postulate you'll often hear, which is kind of covered by some of this already, is the idea, because there are weak interactions, in fact, in ideal gases, right? They have no interactions, that is, molecular attractions to each other. Then the molecules are always traveling in straight lines. So that is, they travel without being like when a meteor goes past the Earth, it's attracted to the Earth, and its trajectory will change. We assume none of that's happening in a gas in kinetic molecular theory. Now, when we describe a gas that behaves in this fashion with these postulates here, right, we call this an ideal gas. And in fact, from these ideas, people are able to derive the ideal gas law from these principles of kinetic energy and temperature and such. All right, so I'm going to skip through the next two slides, which talks about how we get ideal gas law from these principles of kinetic energy and the collision force and stuff like that. And it really does involve a lot of equations. And you'll notice, like, when you get down to here, you stick in R and this PV equals nRT, but then you have to go through all this to get it. And I often find it's really not worth the effort to going through and getting it. Okay, so now, one of the things that you need to know is there's one of the sort of products of analyzing gases in this way is that we get a couple of interesting equations that relate the kinetic energy. Right? This is the kinetic energy of gas molecules to RT. Now, R is a gas constant. The value that we usually use in here is one with joules in it. But R 3/2 RT gives us the kinetic energy of the molecules. And we can also relate the two right sides of the equation here for kinetic energy. This is for a mole of gas, by the way. Kinetic energy, and we can get this equation. So now I'm going to erase all the boxes I have, and really the two equations that you need to be familiar with. That one in part because it shows that kinetic energy is proportional to temperature, and this one because it shows how the velocity, this is molecular velocity, relates to the molar mass and temperature. So you can actually calculate gas molecule velocities using this equation. And there's a number of other interesting applications of this particular equation. So we'll do some examples using this in the upcoming slides. So one of the things that comes out of kinetic molecular theory is that when you have a mixture of gases, so in this particular example, there's oxygen, nitrogen, water, helium, and hydrogen, right? For each grouping of gas molecules, their kinetic energy is the same. So for example, even though what we have listed on the left side is relative number of molecules with indicated velocity, right? And here we have molecular velocity. So oxygen has a lot of molecules that are down here on the graph. It peaks around 300 meters per second roughly. And then there's hydrogen, H2 gas, which is peaking right around 1900 meters per second squared. Well, it turns out when you look at the kinetic energies of these populations of molecules, they're all the same. And the reason they look different is because in order for hydrogen to have the same kinetic energy as oxygen, it has to be moving faster. So within a sample of a gas where all the gases are at the same temperature, right? A gas mixture, where the gases have to all be at the same temperature. They all have the same kinetic energy, but that means they all have different velocities. Hydrogen gas molecules are moving much faster than oxygen gas molecules. And basically the way these curves are distributed is that the heaviest gases have the slowest average velocity, which happens to be, if I remember right, here somewhere where this is pointing, and this one's where the nitrogen's pointing. That's the RMS velocity. Actually, it's the root mean square velocity, but it's like the average velocity of the population of gases. And so it's directly proportional to temperature, but inversely proportional to molar mass. So in a mixture of gases, the average kinetic energy of each gas is the same, which means the velocities are all different. So each gas has its own velocity distribution. And lighter gases on average move faster than heavier gases at the same temperature. Now, the other thing I wanted to point out, that one of the outcomes of kinetic molecular theory is, we don't think about this, but when you have gas molecules in a container, not each, let's just say it's hydrogen gas, right? They don't all have the same kinetic energy. They have the average kinetic energy, which is the same as other gases at that temperature, but there's a distribution of velocities of the gases. So for example, here in hydrogen, let's say hydrogen was the only one in this container. You have some gas molecules which are moving very slowly, and they have some gas molecules which are moving really fast. The average is again about where this thing is pointing. It's a non-uniform distribution. It's not like a bell-shaped curve, if you're familiar with that idea. But even though, so you have, let's say, a distribution of temperatures, not all the molecules are moving at the same velocity. They've done some really cool experiments taking advantage of this by essentially really cooling molecules down to near absolute zero, based on the idea that gas molecules are moving more quickly or have more kinetic energy. They can let certain the high energy gas molecules go and keep the low energy ones trapped. So it's kind of a neat idea anyways. Another interesting idea of kinetic molecular theory is that as you increase the temperature of a gas, right, you increase the velocity of the gas molecules. And so here what we have is a population of gas molecules at 273 at 0 degrees Celsius, right? And here's at 1,000 degrees Kelvin at 2,000 degrees Kelvin. This is, nitrogen molecules over here, and there's their average molecular velocity. But even though you have some really high speed molecules here, and you have some really high speed molecules here, right? What's essentially happening is as you increase the temperature, you're pushing this distribution to the right, is what we say. But even though you're doing that, you still have some molecules in this region which are moving very slowly, okay? So what we're going to do is we'll calculate the RMS velocity of hydrogen at 273 Kelvin using the equation that I showed you, so you can see how the units work out. So to calculate the a gas molecule's velocity, we use the equation mu, is equal to the square root of 3 RT over the molar mass. And there's some tricks with this so that you have to deal with the units. And I'll show you what those are here in a second. But what you really need to know is what value of R do we use. Okay, and the unit for R, 8.314. So it's different than the R you're used to. Joules per mole times Kelvin. Now, this can also be written, joule is actually composed of other units, and it's a kilogram meter squared per second squared over moles times Kelvin. Now, why is it important that I write that out? That unit, right? That's just the unit. It's important that you write that out because you have to realize that the mass unit in your molar mass needs to be in kilograms. So my molar mass for hydrogen is 2.016 grams per mole. And let me write it like this because I have to convert it over. Grams per mole. And there's a kilogram is 10 to the third gram. So it ends up being 2.016 times 10 to the minus third kilograms, like that. So let's go ahead and plug this information in. Oh, my temperature is 273 Kelvin. So let me write that, 273.15 Kelvin. I need to plug that all into my equation. So my RMS, root mean square velocity for the gas, is going to be the square root. And I'm going to write all the units in. That's why I'm putting all this space in here. It's going to be 3 times, right, 8.314. And then I'm writing this out as kilograms meter square per second square per mole times Kelvin. So it's kind of a gnarly looking unit. That's why we write joules as J, right, rather than writing it as its units all the time. But you do have to realize what that is. And we're going to multiply that by the temperature, which is 273.15 Kelvin, all under the radical sign. And then what we're going to do is put the molar mass of hydrogen as 2.016 times 10 to the minus third kilograms. Oh, I forgot to write my mole per mole up here. This is kilograms per mole. I left it off. All right, so let's go through the bother of showing how the units cancel. And this is the importance of why we do it this way, right? The kilograms will divide top and bottom. The moles, 1 over moles, will divide out. I'm multiplying that by Kelvin, so that'll go away. And then I end up with this number. Hang on. Sorry, I looked at the number. I go, that's not right, but it is right. It's 3 the square root, okay, of 3,379,000, right? 418, 379,418, and the units. I'm sorry, the units that are left are meter square per second square. So I did all the math and divided by the molar mass, and that's what you're left with. I have in my calculation actually 4 sig figs. And then I take the square root, and I get 1,838, and it's meters squared per second squared, so now it ends up being meters per second. So a hydrogen gas molecule at 0 degrees Celsius is traveling 1,800 meters per second. And to put that in perspective, what people know, right? Football field's about 100 meters. So in a second, it's going about 18 football fields. So it's pretty fast, right? Supersonic speed, really. It's going pretty fast. Why doesn't a gas molecule kill you when it hits you? Well, it just doesn't have any mass, right? It doesn't have any mass, so it can't impart that much energy. And the other thing to think about is it can't actually travel in a straight line like that because air is full of gases, and so as these molecules are flying around at these velocities, they are actually colliding with each other quite a bit. Anyways, just some cautionary notes, right? Make sure that you use the right value for R. Make sure you know to have your molar mass in kilograms per mole, and your temperature needs to be in Kelvin. And then you don't have to worry so much about getting the units to cancel out every time. You're just going to take it on faith at that point. If you're writing everything in the correct units, that you're going to end up with the answer in the right units.